Now let's try to solve example 1 problem based on what we discussed in the lecture, in the previous lecture. Okay, so I'm gonna give you 15 seconds to have you read this statement, and please think about how you would, solve this problem if you are given this question. Okay, this problem is about a steam turbine where steam enters to this turbine at certain condition and leaves at another certain condition. And let me try to mark what seems important to me while I'm reading this statement. Okay, all right. Steam enters an adiabatic, so that is adiabatic turbine. Okay, which means that heat transfer is not allowed. Now it runs steadily, so that is in steady state condition. The inlet condition of steam is 3 megapascal and 400 degree Celsius. Then let me ask one question. So where is that state located? Is it in a saturated liquid vapor mixture, or is that in the superheated steam or superheated vapor condition? Then how can we find this? In order to find this, you can use either table A-5, that is about saturated liquid vapor mixture, or table A-6, which is about superheated vapor. Let me open up table A-6 for 3 megapascal. And based on this table, the top line here gives us information about the saturated temperature at the pressure of 3 megapascal. Based on this table, we can see that the saturation temperature is at 233.85 degrees Celsius, which is lower than 400 degrees Celsius. So what it means is this one, the condition is in superheated vapor. Then how about the exit condition? So now we have 50 kilopascal and 100 degrees Celsius. And if we do the same thing in table 8A6 at pressure 0.05 megapascal or 50 kilopascal, the saturation temperature at that pressure is 81.32 degrees Celsius. So again, the exit condition is also superheated vapor. Right? Now, the power output of the turbine is 2 megawatt. So we know how much power the turbine is generating. Now, from the given conditions, now we want to calculate the isentropic efficiency of the turbine. And also, we want to calculate the mass flow rate that flows through the turbine. Now, in order to calculate this problem, let's try to assume these two things. So now, as that is already given from the statement, your turbine is steady state condition. And now let's assume the kinetic energy and potential energy change of the steam ignored. Okay. So in order to solve problem question A and B, I'm wondering if you can draw a TS diagram that describes what happens in the turbine. Can you draw it? Okay, then let me try to draw the TS diagram. Right? Because it does involve phase change or near the saturation dome. Let me draw the saturation dome first. Okay. Then we have two constant pressure curve. One is at 5 megapascal and the other one is 50 kilopascal. Now we have set one, which is in a superheated vapor. Then we have exit, the condition, which is also in a superheated vapor. So now let me just draw this point here as 2. So what is a really important thing is that now for adiabatic turbine, and which is an actual condition, your entropy at 2 should be bigger than entropy at 1. So now I can draw this arrow this way. So from 1 to 2. If you have an ideal turbine, then you should have this vertical line, which means here, and let me tell that is to S, that is for very ideal turbine. Now, based on this given condition, let's try to calculate the turbine efficiency, eta T, which is defined as H1 minus H2, which is an actual turbine work, divided by H1 minus H2S. So in order to calculate the turbine efficiency, we have to find out all enthalpy values H1, H2, and H2S. Now, let's try to find out value of H1. So at T1 and P1, okay, I'm gonna write down the enthalpy and entropy because we need entropy later. Okay. Oops. Now, the way we find these two values is by using the table again. In the table A6. At 400 degrees Celsius and 3 megapascal, what you see is enthalpy value here and entropy value here. So H1 is 31.7 kilojoule per kilogram. Please don't forget to write your unit every single time. And the enthalpy, specific enthalpy, is 6.9235 kilojoule per kilogram Kelvin. Now, how about at T2 and P2? Same thing, by using table A-6 at 100 degrees Celsius. Now we also have those values at 2. Okay, let me write it down. H2 equals to 682.4 kilojoule per kilogram. In fact, we don't need the entropy at exit 2, but just let me write it down, which is 7.6953 kilojoule per kilogram Kelvin. Now, we can see that this entropy value at the exit is bigger than the entropy of the inlet, so it totally makes sense. Then how about H2S? How can you calculate it? Okay. So again, this H2S is the exit enthalpy when your turbine is ideal, meaning that when your turbine has an isentropic process. So what we know about this fact is the entropy at the exit of the ideal turbine should be equal to entropy at the inlet, which is 6.9235 kilojoule per kilogram Kelvin. Now, how do you know, and where do you know that point is located? How can you tell the point, the location of the exit of the ideal turbine? What would you do? Now, in order to estimate where that point is located, what it can do is we actually have to compare this entropy with the entropy of the saturated liquid and vapor mixture, and we see the saturated liquid entropy SF and saturated vapor entropy at 50 kilopascal. And from this value, what we now see is that the entropy we know at the exit is in between the saturated liquid entropy and saturated vapor entropy. So from this comparison, we can clearly see that this one is in the saturated vapor mixture. So now this one is smaller than Sg, and that is bigger than Sf. So what I can write is S to S should be able to be calculated from Sf and the quality and Sg. Okay. Now we know Sf to be 1.0912 kilojoule per kilogram Kelvin, and Sg is equal to 7.5931 kilojoule per kilogram Kelvin. So from this equation, we can calculate the quality of the steam that is exiting the ideal turbine, which is 0.897. From the given quality, then we also can calculate the enthalpy of point to S as HF plus X to S, here FG, okay? HFG. Again, from the same table A-5, we have saturated liquid enthalpy and the difference between saturated liquid and saturated vapor enthalpy values. So from those two values, we can calculate, the enthalpy to be 2407.9 kilojoule per kilogram. So we know everything. We know all enthalpy values that are needed to calculate the turbine efficiency. So by using those numbers, now we know that is 0.667, or in percentage 66.7%. Now, how can you calculate the mass flow rate? The turbine is in steady state condition, so we gotta use the first law of thermodynamics for an open system when the system is in steady state condition. So the change of internal energy of control volume, which is turbine, is 0, and that is due to Q dot minus W T dot and plus M dot, now H1 minus H2. We don't have to worry about the heat transfer rate. So what you do know is turbine or m dot can be calculated by the power of the turbine divided by H1 minus H2. That is given, the power of the turbine is given as 2 megawatt. Okay, and we know H1 and H2, so we can calculate the mass flow rate that flows through this turbine using those numbers. That is 3.64 kilogram per second.